Okay, here we go with trigonometric functions. So, there's going to be a small handful of things you have to kind of memorize as we go through. So, the good news is, after we go over this, you're going to want to practice this right away. So, one of the good things about working on the video is you budget out your time. You can set out the time, watch this video, and then immediately jump into the homework and solidify the stuff that we're talking about. So, here's what we're going to look at. Let's use a little blue. So, this line, this ray that we see in front of us here, could be any ray anywhere really, but we'll just use a simple case of here we have this ray starting at the origin and going off at some angle theta in this direction. Now, I've specifically drawn it so that it's a little cleaner to look at, but let's take a look at this triangle. So the one that's built by going over 4 and up 2. Now, if you have over 4 and up 2, then you can easily, based on what we said at the end of the last video, you can easily find this hypotenuse using Pythagorean theorem, so they would call that r. So for the little blue triangle, the r is going to be the square root of 4 squared plus 2 squared. And r in this case is going to be 16 plus 4, that's 20, square root of 20. Okay, we'll reduce that down. R is going to be 2 times the square root of 5. Okay. Great, right? Then if we build another triangle using the same angle, can't stress that enough, we're going to use the same angle, right? We're going to build another triangle that's, say, over 6, sure, and up 3. Now, what would its r be? Well, the r for the red triangle is going to be the square root of 36, that's 6 squared, plus 9, okay, it's 3 squared. So r is the square root of 45, which is going to be equal to, let's see, what goes into 45? 9 times 5, so I think that's going to be 3 squared root of 5? Yeah. Now, okay, whatever, right? So they're getting bigger. Big freaking deal. Give me one more to make, and then I'll drive my point home. So one more, we'll go out to like here, the green one, down. So we'll go over 10 and up 5. And I'm sure you see the pattern that way, but if we find the r for that value, it's going to be the square root of 100 plus 25, which is going to be r is the square root of 125, and I believe that is going to be 5 times the square root of 5. Now, what I wanted to point out is this, is that while they are all different triangles, I think you'd all agree that if in geometry terms we'd call them similar triangles, they're not the same because they're different sizes, but there's something about them that's similar. Well, it turns out that as long as we use for this angle right here, whatever that is, I'm estimating at like 32 degrees. I can figure it out actually using trigonometry. But for that specific angle, if you build a triangle using that angle in that location, and you take any, and I mean like any, you take any x, for example, and any y, and you place them over each other, x over y, anywhere on there, you're going to get the same value. You can probably see that already. For example, if I take 2, the blue triangle, so if I take x over y for the blue triangle is 2 over 4, which is a half, right? For the red triangle, it's 3 over 6, it's a half. For the black triangle, it's 5 over 10, which is a half. Also, it's not just the legs. You could pick a different combination. Remember, we call this side here r, the hypotenuse, so no matter where your r is, if you look at, say, let's go x over r. What would it be for the blue triangle? Well, for the blue triangle, that would be 4 over 2 square root of 5. For the red triangle, that would be 6 over 3 square root of 5. And for the, and of course, if you do the green triangle, you're going to get 10 is the x value over the r value, which is square root of, 5 square root of 5. And of course, every one of those, you'll notice, reduces down to 2 over the square root of 5. It's all the exact same value. Now, we can make all kinds of triangles and the sides will get different, but as long as we're using this angle, whatever that angle is, and we can look that up in fact, I'll probably calculate it here in a second just to prove to you, but this angle is what creates this specific ratio. If you make that angle a little bigger or a little smaller, that ratio of x over the hypotenuse is going to change. As long as this angle is used, this has to be the ratio of x over the hypotenuse. Or this has to be the ratio of the x over the y. Or the another possibility, let's say we've got x over y, we've got x over r. We could do, another possibility would be to look at all of the y over r values, for example. And that ratio would turn out to be the same for all the different triangles. As long as we use this, as long as we use this angle. So these ratios are specific to that angle. They're linked to this angle. Each of these ratios that I've sketched out here, this one, x over y, actually, well, has a name, but that's not the one I really should have used, but that's okay. More appropriate would have been if I had found y over x, but x over y has a name as well. But these ratios, all the possible ones that you could create, y over r, x over y, y over x, or of course r on top for x and y, all of them have a name, their own individual name. And their value is linked to the value of some angle. So, what are their names? If you have the ratio for any given angle, and you create that angle on a coordinate system, and you know the x, a point anywhere on that line. So the point, by the way, let's go back. The points here are all different. Like this point here, right, is the point 4 comma 2. This point here, the red one, is the point 6 comma 3. This point here is the point 10 comma 5. So all those are points on that ray somewhere. If you know any x and y value on there, you could also then pretty easily, using the Pythagorean theorem, find the r value that goes with them, the hypotenuse. So you have 3 values for any point. You have its x value, its y value, and if you drew the hypotenuse, if you drew that triangle and found the hypotenuse, the r value that goes with it. The sine, the thing we call the sine of any angle, is defined as the y over the r. So when you hear sine, you think y. Cosine is x over r. You hear cosine, you think x. That's my advice to you. One of the ways I keep it straight is alphabetical order. Sine comes after cosine, and y comes after x. So they're in the same rough order there. Tangent is y over x. That's why I'm kicking myself, because I put x over y in the last example. I should have done y over x, but that's all right, because these top three, are by far the ones we're going to look at the most. So these 3 right here are kind of the 3 you notice on your calculator. Those are the 3 that you see. You don't really see these because they're easy to find if you know the other ones. So, what are these ones down here below? Well, they are just the reciprocals. So, for example, the cosecant. And I know. It'd be nice if the cosecant's reciprocal was the cosine, but it's not. If you take the sine and you flip it upside down, so if you take the sine here and you flip it up and down, That ratio is called the cosecant, r over y. The secant is defined as r over x. And the cotangent, okay, this one makes a little more sense probably for you, is x over y. That's them. So and if you know an x and a y, you can always find r, or for that matter, if you knew r and you had one of the other ones, as long as you got two sides of a right triangle, you can always find the third, then you can find these ratios, and they are unique to the angle. The cosine of 30 degrees is some number. No other angle can have that number as the cosine, unless it is got, like cosine of 30 would be here. So with this angle one could, because the cosine of 150, because it ends up being the same triangle. But unless it's that, you're not going to get the same value for the cosine. And don't worry, we'll get to that in a moment. So, this is something you're going to need to know. Flat out, you have a week or so, or a few days, to make sure that you commit these to memory. I cannot stress it enough. All right, you need to know those. This would be the same. So the purpose of this slide is to point out that that angle doesn't have to be up here in the first quadrant. It could be the angle that we see here. It could be down in the third quadrant or the second or whatever. No matter what the angle measure is, you'll end up making a right triangle using your x. Use this triangle, the one I'm drawing. All right, I'll always do the x first along the axis, then the y off the axis. Your x value and your y. Do not, and I'm going to say this again just in case you're not listening, do not, when you think of this triangle and this trig stuff, don't use the triangle, don't go up or down on the y and then over in the x. Don't use that triangle. It'll confuse you because things will get reversed and so forth. We are always going to make the triangle that is connected, shall we say, to the x-axis. But it would, all the same stuff would apply here. The sine of this would be the sine of the y over the r value. We'd have to find the r. This is probably a good time to point out that the r, if you think about it, when you go to find r, you got to take the square root. R is always going to be positive. X and y can be negative, like for example down here, they're both negative. But r is always positive. So, if we have, typical problem, if you're given a point like this, 5, 12, so we go over 5, and we go, really, 12? Really? I don't even have a 12 on my thing. All right, the hell with 5, 12. Let's go 5, 8. Something a little easier for me to draw. There we go, better scale. So if I go 5, 8 would be right here. All right, so I got 5, 8. So if I'm going to use that point, then what we're going to imagine or look at here is a ray or a line that goes from, let's see, from the origin to that point, like so. And we're going to also envision, if you'd like, the triangle that goes, remember, x-axis, along the x-axis, and then up like this. And the r, the hypotenuse, is this length. Of course, your x value is 5 and your y value is 8. So if we're going to find the sine, cosine, tangent, cosecant, secant, and cotangent, somewhere in there we're going to need the one thing that we don't have, which is the r. We don't know this r right now. We have an x and a y, which means we have the legs of this right triangle. So first thing we're going to do is find r. R is going to be the square root, of course, of 5 squared plus 8 squared. Which just means r is going to be the square root of, let's see, 25 plus 40. R is going to be the square root of 40. What the heck? 40. Who does 8 squared and get 40? I'm obviously tired. 64 maybe? That would work. 5, 6, 7, 8, 8, but that's a square root of 6, 7, 8, 89? 25, 64, I should probably the calculator out, and so yeah, 89. Okay, and I don't think there's anything that goes in there, so we're just going to leave it as 89. So that means I have x is equal to 5 y is equal to 8 and r is equal to 89. I can now make all of the trig functions. Best if you try to do it from memory here. So sine is, I'll give you a second to think. That's right, it's y over r. So we're going to use, it's going to be 8 over the square root of 89. Square root. We'll talk about rationalizing that denominator. We can't have the square root in the bottom because math people don't like it, blah, blah, blah. But what's the cosine going to be then? Well, the cosine, think about it, is x over r, so that's going to be 5 over the square root of 89. And the tangent is the y over x, so it's going to be 8/5. And then to find these guys, I've conveniently located them next to their reciprocals. But of course you'd have to know that that's what they are, and you just flip them upside down. So you're going to go flip them upside down, you're going to get square root of 89 over 8, square root of 89 over 5 for the secant, and 5 over 8 for the cotangent. Now, real quickly, let's look at this. We're not really allowed to have a square root of 89 in the bottom there. Let's have a square root in the bottom. So in order to get rid of that, of course, we multiply top and bottom by the square root of 89. That will produce just a plain old 89 in the bottom. And the top, I'll have 8 times the square root of 89. And now, that is the value that MyLabs Plus and people that have problems with such things will accept as your answer for this. Take a second. See if you can figure out this one that I'm circling. See if you can do the same process to it. I'll give you a few seconds. See if you can, or maybe you should just pause the video. That way I don't have to wait. Let's do that. So pause the video and see if you can do that one, and then restart it and see if you get it right. Welcome back. We're going to do this one here. We're going to do it in blue to keep it consistent. So I'm going to do 5 over the square root of 89. Multiply top and bottom by the square root of 89. And I'm going to get 5 square root of 89 over 89, and I'm done. That is rationalized. Pretty soon you'll be doing that so quick you won't even realize you're doing it. All right, same thing here. We're going to go, let's see, negative 3. And then I'm going to go up the square root of 3. That's, let's see, 1 point something. So somewhere in here is the point negative 3 comma square root of 3. So I have the x, the negative 3. I have the y, which is positive square root of 3. I need the r. Well, the r is going to be the square root of negative 3 squared, but the negative really doesn't make a difference because I'm going to square it anyway, so it's going to disappear, plus the square root of 3 squared. So that's going to be r equals the square root of 9 plus 3. Squaring the square root gets rid of that, so we get 9 plus 3 is 12. So r is going to equal the square root of 12, which when we take out the 4 that goes into 12, that's a perfect square, we'll get 2 square root of 3. So my values are x equals negative 3, y equals positive square root of 3, and r is equal to 2 square root of 3. And I go ahead and from memory, I try to put in all the different things. So I'll give you should probably pause it and try them on your own real quick just to see, but let's give it a shot here. So we're going to go, sine is going to be square root of 3 over 2 square root of 3, which is just a half. Ooh. Cosine is going to be negative 3 over 2 square root of 3. And the tangent is going to be y over x is going to be square root of 3 over negative 3. Cosecant is going to be 2. The secant is going to be 2 square root of 3 over negative 3. Cotangent is going to be negative 3 over square root of 3. Now if I go ahead and I rationalize all the denominators I need to get, I'm going to have, let's see, ooh, this one's going to be interesting. So let me circle it in red. We're going to do this one up here because I need some space. So we're going to take negative 3 over 2 square root of 3. Multiply top and bottom by that square root of 3. That's going to give me 2 times 3, which is 6 in the bottom. And up top, I'm going to have negative 3 square root of 3. But 3 goes into 6, so I can reduce that. That's going to be negative square root of 3 over 2. And the tangent is going to come out to be, oh no, tangent's good. The cotangent is the one that needs to be rationalized. It's going to be 3 square root of 3 over 3, negative. They're going to cancel, so it's just going to be the square root of 3, negative square root of 3. Okay, so if you're in the second quadrant, out here somewhere, in order for this to be positive or negative, well, first of all, what have I said about r? R is always positive. So really, the question is x negative in the second quadrant? Well, yes, right? Over here, x is negative. X would be negative in the second or third quadrant. So it is going to be negative. In the fourth quadrant, once again, this is always positive. So it's up to the x, and in the fourth quadrant, x is positive. So r over x is positive. Okay, so strange. This thing right here, when you get to this on the homework, this is what they want. First of all, we'll come back to this part that I'm circling in a moment. All right, we'll come back to that in a second. First thing I want you to do is get a feel for, or is to graph this line, but let's graph it. Let's graph it by solving it for y. So I'm going to have negative 6x minus y equals 0. I'm going to add y to both sides and get negative 6x equals positive y, or the line, I'll write it over here, y equals negative 6x. And I'm, for effect, plus 0. Okay, right, so it goes, its intercept is the origin, right down here. And the slope is negative 6. So I would go, let's see, it's going to have a negative slope, so we'll go up 6 and left 1 here, or down 6 and right 1. Now normally I would say, all right, go ahead and just sketch your line. I'll do it real quick. So normally I would say, boom, there's your line, roughly. But we want to, oh, really? But we're going to be, we got to be a little smarter here in the sense that we got to, whoops, oh my goodness, is that we got to notice that they only want the part that's less than 0. So they don't want anything where x is bigger than 0. So they don't want this. They just want that right there. They want this part. Okay, now it looks like a ray like we've been dealing with. In fact, I should probably draw it like a ray. Let's do that. Let's do here, we'll do pink, what the hell. Boom, there we go. They want that. Okay, so that's all well and good. I need just one point anywhere on that line. We can do that. Here's the angle in question, right? And the point I'm going to use is the one I made, one of the ones I made to make this thing. That's the point, let's see, negative 1, and then up 6. So that is the point negative 1 comma 6. And in order to get these guys over here, I need to find r. And r is going to be the square root of negative 1 squared plus 6 squared. It's going to be 36 plus 1, that's 37. So r is going to be the square root of 37. So if r is the square root of 37, the x I'm going to use doesn't really matter. I use any point on that line. But the x I'm going to use, I chose to use, is negative 1, and the y I'm going to use is 6. Then we'll go through and find all the different values. So sine is going to be 6 over the square root of 37. Cosine is going to be negative 1 over the square root of 37. Tangent is going to be 6 over negative 1. Cosecant, flip them upside down. Square root of 37 over 6. Square root of 37 over 1. and negative 1 over 6. And then, last step, of course, any of them that aren't rationalized or have a square root in their denominator need to be rationalized. So sine, for example, is going to become 6 times the square root of 37 over 37. That's a 7. And cosine is going to be the square root of 37 over 37. And I think that's all of them. Everything else, okay, yes, we can write this one as negative 6. We can write this one as just square root of 37. We don't need to write it as a fraction. So if you know an x and a y, you find an r, boom, you can just write out the ratios. That's all there is to those. All right, let's look at a few weird cases. If you recall, the quadrantial, I don't know how to say the word, but anyway, it doesn't matter, are the ones along the axes. So 0 degrees is one of them, 90 degrees is another, 180 is another, and 270. So what happens when an angle is one of those four? All right, so what happens when our angle is, let's see, either 0 degrees or 360, 90 degrees, 180 degrees, or 270 degrees? What are the values of sine, cosine, and tangent? And for that matter, then we could flip them upside down to get their buddies. But let's just do sine, cosine, and tangent and just recognize we can always take their reciprocals later. So what's the sine of a 180 degree angle? What's the cosine of a 180 degree angle? What's the tangent? Likewise down here, what's the sine, the cosine, and the tangent of 270? So let's consider those. So here's the weird thing. Here's what happens. Let's go with, use a dotted line. So if this is my r, right? And the green will be my x. As r gets closer and closer to that axis, the y gets smaller and smaller and smaller. And then when it finally reaches the axis, the y value at this point, oops, we got this, don't worry, don't panic. The y value at this point is 0. And the x and the r are the same. They match up. They lie right on top of each other. So it's really no longer a triangle. But the key is, here, he says, he has to point. So here, at this point, this is true. When it's along here, the x has to be 0. And the y and the r are the same. And similar things are true here. On this side, it's very similar to this. The y is 0. Right? The y along this axis, y is 0. So that's true. But the value of the x is going to be the opposite of r. So whatever r is, the x is going to be the negative value of that. Makes sense. You're over here in this quadrant, all right, where x is negative. So similar argument down here. It's going to be like this, but some sign changes here. So we're going to go, at this point, x is 0, and y is equal to the opposite of r, negative r. So now let's look at our trig values. What would the sine be? If the y is 0, I really don't care what r is then, do I? Because if the sine is 0 over r, 0 divided by anything is just 0. So it is not at a 0 degree angle or a 360, the sine of a 0 degree angle is in fact 0. What about the cosine? Well, that's going to give you, cosine's defined as x over r, but they're the same thing. So anytime you divide by the same thing, you just get 1. So the cosine at a 0 degree angle is actually 1. And the tangent, well, the tangent's going to be y over x. That's going to be 0 over x I don't care what x is because 0 divided by anything is 0. So the tangent is also 0 at a 0-degree angle. Okay, so let's do a similar process at a 90-degree angle. Cosine of 90, sine of 90, and the tangent of 90. The sine is y over r, but in this case, y and r are the same, so that's just 1. So here, the sine, notice the y value would be positive 1 in this direction. If you went up just 1, oh, Jehoshaphat's. I got this. There you go. The cosine is going to be 0 in this case, because it's going to be x over r, but x is just 0, so that's going to come out to be 0. And the tangent, well, the tangent's kind of funky, isn't it? Because tangent at this point would be y over x, that would be y over 0, and that's undefined. So the tangent is undefined at that location, at 90 degrees. If we come over here to 180, you notice, by the way, we're looking at ones, zeros, or undefined. So that's when you're at these quadrantial angles or whatever, at these locations along the axis, your sines, cosines, and tangents are going to be 1, 0, or undefined. So the sine in this case is going to be 0, the cosine is negative 1, and the tangent out here is going to be 0 as well. And down here, at 270, I have a sine of negative 1, the cosine is 0, and the tangent is again undefined, because the tangent would be x over y, but so it would be y over x, my fault. So the tangent's y over x, but in this case x is 0, right? You don't go up or down here. You don't go left or right. I mean, you just go up or down. So you would have undefined. You'd have y over 0, which is undefined. Okay, so the secant of 90 degrees. Don't freak out. Don't freak out. First of all, where's 90 degrees? It's down here, right? You go from here this way to 90. So it's the same location as positive 270, right there, where that red arrow is. Second thing you don't want to freak out about, secant. Whatever. I'm going to find what's the reciprocal of secant? That's what you want to know. Reciprocal of the secant is cosine. So I'm going to look at the cosine of a negative 90 first, and then I'll figure it out from there. So the cosine of negative 90 in this case would be, let's see, that's where the x is 0, right? So down here, so the cosine would be 0. So that means the secant, which is 1 over that, would be 1 over 0. Well, there's only one way to describe that. That'd be undefined. So the approach was figure out where you are. I'm just down here at this negative y-axis. I know at that point that the cosine of that angle, negative 90, or you can look at it as positive 270. They're coterminal, right? They're the same angle. The cosine at that location is 0. Well, the secant, by definition, is the reciprocal of the cosine. If the cosine is x over r, the secant is defined as r over x, which actually, later on we'll look at, but you can, if you want to, look at it like this. The secant is always going to be 1 over the cosine. They're reciprocals of each other because of the way they're defined. All right, so this problem looks nasty, but we're going to take care of this because we'll look at this one first. So we'll do that one in red. So we'll do this in red. We'll analyze the cotangent of 270 in red, and we'll analyze the cosine of 0 in blue. So at 270, it's down here. Cotangent. Instead of cotangent, let's look at the tangent. What do I know the tangent is at that point? But the tangent of 270 is undefined. That means it was y over x, but the x was undefined, so it was y over 0. If I flip it, I get 0 in the numerator now. So the cotangent would be 0 over y, 270, which is just 0. So this in red is really just 0. 5 times 0, okay, we'll get to that. Now what about the cosine of 0 degrees? Well, cosine of 0 degrees is going to be, let's see, that's where the x and the r are the same, so the cosine here is just 1. So this thing comes out to be 5 times 0 minus 6 times 1. It's negative 6. You see a problem like that on the test. I think there are one or two like that, or in the homework for that matter. They're going to come out to be, because they're going to use probably quadrantial angles. So you notice 0 degrees, 270. They're going to come out to be zeros, ones, probably not even undefined, because then you can't really do the problem. So they're going to come out to be zeros and ones or negative ones. So the answers won't be that hard. It's not like a lot of fancy calculations. So likewise, cotangent of 270. So we'll do this one, and we'll look at that one in blue, this one in red, and we'll look at this one in green. So in blue, he says, blue. 270's down here. Tangent at 270 is undefined, which means that cotangent at 270 is 0. So that's 7 times 0. Now we'll do the one in red, 180. So over here, 180. Now secant, what do I think of? When I see secant, I want its reciprocal to work with. So there is secant, the reciprocal is cosine. So the cosine of 180 would be what? The cosine of 180 is negative 1. And the reciprocal of negative 1, so the secant of 180 would be the reciprocal of that. Negative 1 flipped upside down, but that's still negative 1. So this whole thing here comes in to be plus 1 times negative 1. And then in green, cosecant of 270. So I'm back down here at 270. Cosecant is the same as the sine. So the sine at 270 is negative 1. The cosecant at 270 then is the reciprocal, which is negative 1. This 2, now comes something new. This 2 that you see here, this 2 that I'm using the giant arrow to point at, this 2, what that is telling you is to square whatever you get when you take the cosecant. In other words, another way of writing the exact same thing would be to write 7 times the cosecant of 270 squared. But it is understood by math people that if you write it there, it means what you see right there below. So we have negative 1, right? That's the cosecant of 270 is negative 1. If you square that, you just get positive 1. So this whole thing boils down into 7 times 0 plus 1 times negative 1 plus 7 times 1. Well, that's gone. That's just 0. So I have 1 times negative 1 is negative 1 plus 7. That's 6. Okay, so they give us the cosine of an angle is 7/8. And we're supposed to find the secant. That's not that hard. Be careful. This is actually a very easy problem. Because if you understand that the cosine of an angle is the x over r, and you remember that the secant of the angle is just r over x, then all we have to do is flip these upside down. The secant of that angle is going to be 8 over 7. You just got to recognize in that case that the secant and the cosine are reciprocals of each other. So if you knew the cosine of an angle, you could just do 1 over that and you would get the secant. If you knew the secant, you could do 1 over that and find the cosine. They are reciprocals of each other. Let's look at a slightly harder problem. Not quite yet. So, reciprocal identities. In other words, the idea that sine and cosecant have the same sort of behavior as cosine and secant. In other words, if the sine of an angle is equal to 1 over the cosecant of that angle, they are reciprocals of each other. Or, the reverse is true. The cosecant of an angle is equal to 1 over the sine. So, if we know the cosecant, all we have to do is flip this upside down, and we'll have the sine. Now, of course, we'll have to rationalize. That's going to be 2 square root of 27 over 27. Sines of trig functions. We already got a good feel of this because, if you recall, since r is always positive, sine of theta, of any angle theta, is defined, of course, as y over r. But since r always has to be positive, right? Since this always has to be positive, the sine will be positive anytime y is positive, and the sine will be negative anytime y is negative. So when I ask you where is the sine negative, you're really just asking yourself where is y negative. All right, well, the sine will be negative here in the third quadrant, and the sine will be negative there in the fourth quadrant, anywhere down here, right? Y is negative. So then it would stand to reason that where would the cosine of an angle be negative? Well, the cosine will be negative anywhere x is negative. So let's see, that's going to be cosine is positive here, right? So the cosine is going to be negative here. And the cosine is going to be negative, of course, in the third quadrant. Well, let's put in where the sine's positive, too. Of course, the sine would be positive here. Actually, let's do it above. And cosine would be positive over here in the fourth quadrant. Now, the interesting one is tangent. Because tangent of an angle is y over x. So whenever they're the same sign, tangent will be positive. Well, that's fairly obvious in this first quadrant. Okay, yeah, they're both positive, so tangent's positive. But where else are they where else is tangent going to be positive? Where are x and y the same sign? Well, that would be the third quadrant. So it's some people get, everything should be negative in the third one. No, not tangent, because tangent's going to be y over x. If they're both negative, that's a positive. So the tangent's positive in those corners, and the tangent is negative in these corners, the upper left and the lower right. Because in those, one of the two, x and y, is negative, the other is positive. Okay, so all we got to do is identify the quadrants and we're good to go. They just want the signs, they don't want the values here. So 295 is in the fourth quadrant. So in the fourth quadrant, x is positive, y is negative. So that means sine is negative. Its reciprocal, cosecant, will be negative. Cosine's positive, so its reciprocal, secant, will be positive. Tangent will be negative because the sine and cosine, they have different signs, right? The x and y's have different signs. So that's going to make that negative, which will also make the cotangent negative. 204 degrees is in the third quadrant. So sine and cosine will be negative because x and y are negative there. That means cosecant and secant will be negative. But tangent, interestingly enough, because it's in the third quadrant, negative divided by a negative will be a positive. So when the x and y are both negative, they'll actually divide out to make a positive. So the tangent and the cotangent will both be positive. 115, that's in the second quadrant, where sine is positive, the x's or y's are positive, and x's are negative. Tangent will come out negative. Cosecant will do the same thing as the sine. The secant will be the same sign as the cosine. Cotangent will be the same sign as the tangent. So, quadrant or quadrants. So you need a place on this coordinate system where the sine of an angle, that is just an angle, could be theta, they used alpha, okay, whatever, Greek letter, your choice, I guess. But where we want the sine of this angle to be positive and the secant to also be positive. Well, the sine goes with y, right? So wherever y is positive, right? So we need, that would lead it down to one of these two. So either this one or this one. All right, in both of these, the sine would be positive. So not down here. It's got to do both. Now, secant. What about the secant? Well, don't think about the secant. Think about the cosine, because the secant and the cosine will have the same behavior here. So wherever the cosine is positive is where we're looking for. Well, the cosine works with x, and it's only positive. That's an ugly pen. We're going to go here. The secant, along with the cosine, is going to only be positive here. The secant will be negative over here. So this won't work. The only place they're both positive is in the first quadrant. Ranges of trig functions. Okay, so the only ranges I really want you to know is, and when you think ranges, think what's the biggest value that a trig function can be and what is the smallest? Well, if you think of the sine and cosine, both of them have the same range. If you have, let's look at the sine, it's y over r. Well, r is a hypotenuse. There, in a right triangle, no side is bigger than the hypotenuse. So there's no way this could possibly be more than 1, because that would mean one of the legs would have to be bigger than the hypotenuse. That doesn't happen. So the same argument is for x, right? Because you're still looking at the hypotenuse. So sine and cosine. This you need to know. You will not get a sine or cosine value out of your calculator. For example, if you go sine or cosine anything, it will always be between -1, right? And so let's see, what do we want to do? The sine of any angle will be bigger or equal to than -1, or smaller than or equal to 1. Cosine, same deal. The range of the sine and cosine function is between 1 and -1. I guess we could just put it like this. -1, comma 1, right? Interval notation. So the range, this is be the range of either the sine or the cosine function. Now, if you consider the ranges of the secant and cosecant, because they're just reciprocals, well, kind of the reverse is true with them. R was always going to be biggest, so they can secant and cosecant can never be between 1 and -1. So, for secant and cosecant, you're going to have negative infinity all the way up to -1. You can include -1, yep. And then combined with, can you jump over anything between 1 and -1? So you're going to go from 1 to positive infinity. So this would be the range, and this is less important to know for sure. This right here, you need to know, I would think. Helpful sometimes to realize, oh yeah, I can't get a value more than 1 for sine or cosine. The secant, cosecant, and then of course for tangent and cotangent, the range is all real numbers, it turns out. So negative infinity to positive. So, based on what we just talked about, there's no way. You can argue this a lot of different ways. I think maybe one of the, depending on what, let's say all you know is what I told you needed to know, which is the cosine, for example, can't be bigger than 1 or less than -1. So, why did I mention the cosine? Because I know that the cosine of this angle will be 1 over 0.2. If you do 1 over 0.2, you get the cosine of an angle is, I believe, that comes out to be 5. But my understanding tells me that there's no way a cosine can ever come out to be bigger than 1. So this is this is impossible. If you memorize it, you would know, okay, so I know that the secant, let's find it here, boom, boom, that the secant and the cosecant, they can't be less than 1. They can't be between -1 and +1. So that's another way to look at it, but I can always reinvent the wheel if I have to. Okay, so this is kind of an interesting problem here. Let's do this. Let me pause the video here because we've been going for a while, and then we'll pick up with a new video.